Hello everyone, I'm Mahdyar Ravanbakhsh, presenting our work, a consensual collaborative learning method for remote sensing image classification under noisy multi-label. On behalf of my colleagues, Ahmet, Kerem, Aksoy, Tristan, Kreuziger, and Begüm Demir from Remote Sensing Image Analysis Group at TU Berlin. Multi-label remote sensing image scene classification methods aim to automatically assign multiple land cover class labels to each remote sensing image in a given archive. Methods based on deep neural networks have shown strong performance gain in remote sensing multi-label scene classification problem. Most of deep models requiring a large number of reliable training images annotated by multiple land cover class labels. However, collecting such data is time-consuming, costly, and needs expertise. So, what we can do? A solution for having a training set with zero labeling cost is to use publicly available thematic products as labeling sources. Thematic products, which known also as digital maps, covering wide areas and can be used to generate training sets at large scale for remote sensing problems. Thematic products can be in country, continental, and global scale. For example, on a continental scale, current land cover maps are one of the most accurate products at the European level. However, all of these thematic products, if used as a labeling source, can produce noisy labels. This is due to several issues. First, there can be errors in the map depending on the strategies that used to generate the map. For example, accuracy of current maps is about 85%. Or the noise can be due to changes in land use land cover after the construction of the maps. And finally, the geolocation errors due to the residual misalignment between a digital map and a satellite image, which can easily generate error. Therefore, using the thematic products as labeling sources can lead to produce training sets with noisy labels, which can easily distort the learning process of any model. In general, two types of label noise can be present in multi-label image. Noise associated to missing labels, which occurs when a land cover class label is not assigned to the image, but it is present in the image. Like in this example, industrial or commercial unit label is missing. Another type is noise associated to wrong labels, which happens when a land cover class label is assigned to the image, but it is not present in the image. For example, here, coniferous forest label is wrongly assigned to the image. Both types of label noise can negatively affect the learning process. Therefore, there is a need for methods that are robust against both types of noise without any prior assumption on the type of noise. So in this work, we address this issue. The goal is to identify the samples with noisy labels automatically and without any prior assumption, and also train a classifier that is robust against both types of label noise. To this end, we propose a novel consensual collaborative learning method for multi-label images, in short, CCML, which can identify the possible noisy labels by introducing a novel ranking function and estimate the label uncertainty based on the aggregation of two collaborative networks. Furthermore, our proposed CCML can be used with any classifier for detecting the potentially noisy labels assigned to the training images with multi-labels. To this end, our proposed CCML includes 4 modules. Discrepancy module, which aims at forcing the two networks to learn diverse features while achieving consistent predictions. Group Lasso module, which is proposed to automatically identify the images with noisy labels and also the type of label noise by computing a sample-wise ranking loss. Flipping module, which flips the identified noisy labels, and finally the swap module, which its first task is to exchange the ranking information between the two networks and then to exchange the images with extremely noisy labels from the backpropagation. And now let's move to the details of each module. The discrepancy module is one of the essential modules in our CCML. This module aims to force the two networks to learn diverse features while obtaining consistent predictions. To this end, the discrepancy module consists of two loss functions. First, the disparity loss, LD, which makes sure that the networks learn distinct features. This loss is calculated between the chosen layers of the two networks. And then the second loss function is the consistency loss, LC, makes sure that the final predictions of the networks are similar. Therefore, it is inserted at the end of the network. The only difference between disparity and consistency loss is where they are inserted into the networks, and the fact that one is maximized and the other minimized. In our discrepancy module, we use the maximum mean discrepancy algorithm to diverge and converge two networks, where the logits of the two networks are considered as two distributions and mapped into a kernel space to measure their distances. The next module of our CCML is the group Lasso module, which aims to identify potentially noisy labels in the training set and also identify the type of label noise. To this end, the group Lasso module uses the prediction from two networks and computes a sample-wise ranking loss. The group Lasso includes two terms. The first loss term, indicated by yellow color, calculates an aggregated loss based on missing class labels, while the second term, indicated by purple color, calculates an aggregated loss for wrong class label assignments. We calculate group Lasso for both networks for any given batch of training samples. The group Lasso not only provides sample-wise ranking loss, but also provides information about the potential noisy labels. This information is provided through a ranking error function, E. The ranking error function gives a measure of the potential noise in a class combination. In the case of an accurate prediction, the ranking error is equal to 0. Otherwise, the ranking error function returns a positive value, which indicates noise in the label. The ranking loss and ranking error information will be used as input for the later modules. As an example, given a mini batch including 5 samples, the group Lasso module calculates a ranking error for every label pair in each sample. You can see the ranking error values for each labels here. Then, labels with maximum ranking error values are selected as potential noisy labels. And finally, group Lasso outputs the identified noisy labels of each sample and the sample-wise ranking loss values for sending them to the next modules. So the next module in our CCML, which is flipping module, uses both ranking loss and identified noisy labels to flip the potential noisy labels. To this end, flipping module includes two main components, noisy class selector and noisy class flipper. In detail, outputs of the group Lasso modules from both networks, F and G, are input to the flipping module. The noisy class selector component aggregates the ranking loss values from both networks and selects the samples with the highest ranking loss values as potential noisy samples. Then the noisy class flipper component flips the identified noisy labels in the selected samples. So we should note that the flipped labels are later used for calculating the final loss instead of the originally associated labels. Another important module in our CCML is the swap module, which aims at exchanging ranking information between the two networks. The swap module uses the group Lasso ranking information and binary cross-entropy loss to eliminate the detected noisy labels from backpropagation and exchange this information between the two networks. So, in detail, swap module adds binary cross-entropy and ranking loss values for all the samples in the mini batch and then sort them, and then exchange this ranking information between the two networks. In this way, the network F uses R samples associated with the lowest loss values identified by the network G to update its weights by minimizing the final loss BF. And similarly, network G uses the top-ranked R samples which are associated with the low loss values identified by network F to update its parameter. The final loss is the sum of binary cross-entropy loss calculated over the lowest loss value samples, the consistency loss, and the disparity loss from the discrepancy module. In order to evaluate the proposed CCML, we conducted an experiment on the island subset of big ResNet benchmark archive. We also eliminated 5 classes that were represented with a very small number of training images in the dataset. We select ResNet and DenseNet models as baseline for evaluating the proposed CCML. These architectures were also considered as backbone for the collaborative networks in our CCML. The swap module sets to use 75% of the samples from each mini-batch, which were associated with the small loss values for swapping. For noise injection, we randomly select n% of samples from each mini-batch and flipping n% of the labels from the selected samples randomly. As an example, in a mini batch of 6 samples, when the noise injection rate is 50%, we select 3 samples and flip half of the labels from each selected samples randomly. So, for the first architecture, we use ResNet as baseline and also the backbone for our CCML. We compared them in terms of precision recall and F1 score. As we can see, the proposed CCML improves the multi-label classification performance of the baseline architecture in all metrics. Furthermore, we can see that as the injected synthetic noise rate increases, the gap between the baseline model and CCML increases. This shows the robustness of the proposed CCML against the high noise rate. We also evaluated different architectures. We used DenseNet as a baseline and also the backbone for our CCML. As we can see, the result follows similar pattern. The experiments over different networks architecture demonstrate the capability of our CCML to reduce the negative effect of label noise independent from the selected backbone architecture. We also analyzed the class-based performance of the proposed CCML and the ResNet baseline model. In some classes, baseline and CCML performance are comparable over lower rate of label noise. However, the proposed CCML maintains relatively high performance under high noise rates compared to the baseline model, which demonstrates the stability of the proposed CCML under high noise rates. Furthermore, we observed that the classes with a small number of training images are more affected by the label noise compared to the classes presented with a high number of training images. So, in this work, a novel consensual collaborative multi-label learning method has been presented to overcome the adverse effect of multi-label noise for classification of remote sensing images. The proposed CCML is promising since it can automatically identify 2 different types of multi-label noise without making any prior assumption and achieves high accuracy under high synthetically added noise rates. Furthermore, CCML is architecture independent and can be used within different network architectures, which makes it not limited to the classification task only, and it is applicable in a range of remote sensing applications. In our experiments, we observed that CCML may reduce classification accuracy when the rate of the label noise is very small. This is due to excluding a fixed percentage of the training samples from backpropagation. As a future development, we plan to extend the proposed CCML with an adaptive ranking loss function to adjust the amount of the sample removal. I hope you enjoyed the presentation. In case you are interested, please check out our code and models available under this link.